So in this video we will use Reynolds transport theorem for the conservation of momentum. So let's say we have a volume of fluid moving with some velocity u. Okay. So this velocity comes into being because of the various forces acting on the identified volume. So the forces are surface forces, we have seen this earlier as well, and volume forces. Volumetric forces may be gravity and so on. Okay. So the manifestation of surface force comes through the description of a stress tensor dot the normal vector. Okay. So let's first write down the Newton's second law. Okay. Before all that, we recall that the anyway, we don't need to, we'll see that. So we have on the left hand side ddt of integral rho u dv. This represents the total change in momentum of the identified volume. This is equal to summation of all the forces acting on the volume. Okay. So this identified volume moves with a velocity equal to u. Okay, this volume moves with a velocity u. It is only then when we can apply the conservation of momentum. If the volume is not moving with the velocity u, we cannot apply this law. Okay. Reynolds transport theorem in general says ddt of integral f dv is equal to integral del t of f dv plus integral f u not u b dot n cap dA. Okay. B is some arbitrary velocity and is not equal to u in general. This statement is always valid, as we have derived in the video of Reynolds transport theorem. So these integrals are over starred quantities. And we also have ddt of integral f dv. So let us substitute f by m into u. M into u represents, not m into u, rho into u. Rho into u represents the momentum. And thus we obtain ddt of integral rho u dv over a volume not moving with the fluid is equal to del t of rho u dv plus integral rho u b dot n dA. Okay, this is the quantity and this is the flux. Okay. At the time instant, the two frames coincide. At the time instant when the two frames coincide. So by frames I mean, okay, before that let's just write down the statement for the Reynolds transport theorem for a volume moving with the fluid velocity. So the star implies that the volume is moving with some other velocity. There is no star here, it means that the volume is moving with the velocity of the fluid. So in this case, when B frame and U frame coincide, this term and this term of the two expressions are equal. The temporal change terms are equal. Okay, but we have already seen that this term is equal to summation of f. So summation of f is equal to integral v del t rho dv plus integral rho u dot, there is no dot over here, so it's this term fluxed over the area. But this term is also equal to this term minus of this term, because we can write this particular term as this minus this. So this is equal to ddt of integral rho u dv minus integral rho u b dot n dA, and this term comes over here, plus integral rho u dot n dA. So we then ultimately we can write ddt of rho u dv of the volume moving with the velocity b plus integral rho u minus b dot n dA is equal to summation of all forces. So these terms are both all evaluated for the control volume that we have defined moving with the velocity b is not equal to u. So this is the relative velocity of fluid with respect to the control volume. Okay, so this is how we can derive the conservation of momentum for such problems. So the examples will make it clear on how to apply such equations to control volume. So the derivation of both mass and momentum may look abstract to you, but once you apply this to well-defined examples, it will be abundantly clear on how to apply these ideas to actual problems.